Hey guys, welcome back to chapter 18. In this short video, we're just going to get to know entropy a little bit better, again, qualitatively. And what we're going to look at are properties that affect entropy. So we're going to talk about three properties that affect entropy, at least for now. So these would be properties that we could look at if we're comparing two different molecules, and trying to determine which one is messier, okay, or more dispersed, more spread out, okay? So one thing to keep in mind here is more motion equals more entropy, okay? And entropy, again, is the measure of disorder or the measure of messiness. So if particles have more freedom to move around, they will disorganize themselves if given the opportunity. So things that affect the entropy are size, rigidity, and temperature. So molecular size, the larger the molecule, the more internal motion that there's going to be. So if we think about the following two molecules, so if we think about H2O versus H2Te. So what do these two particles have in common? So both of them are have two hydrogens. Both of them are bent molecules. Both of them have the same number of lone pairs. So oxygen and Te are in the same family, and therefore all of the bonding is relatively the same. The big difference is the bonds are longer as the molecules get bigger, okay? So a longer bond is going to give us more opportunity for motion. So the different kinds of motions that we see are translation, rotations, vibrations. So if we've got a bond over here that's this big and a bond over here that's this big, you can see the amount that this can move back and forth. So think squeeze in, go out, squeeze in, go out, squeeze in, go out. That's going to be a bigger movement or opportunity for movement than this teeny tiny bond over here. We're just going to squeeze, go back, squeeze, go back, squeeze, go back, squeeze, go back. Okay. So the bigger the molecule, the more opportunity for motion, the more opportunity for messiness, even rotation. So if you think about rotating this molecule, it's going to be a bigger rotation than this teeny tiny molecule here. Okay. Larger the molecule, more internal rotation. We can also look at the structure for larger molecules. So not just necessarily the bonds within the molecule, but we could also look at the number of bonds as well. So here we've got some organic molecules. And what you'll see in organic molecules is we like to chain a bunch of carbons together. So in the first molecule, we've got one carbon and it's got 4 hydrogens around it. In the second molecule, we've got 2 carbons that are connected together, 4 hydrogens or 3 hydrogens around those. In the third molecule, it's 3 carbons. Fourth molecule is 4 carbons. So all we're doing here is just adding a link to the chain, adding a carbon to the chain. And what we see is as the molecule gets larger, there's more internal motion within that molecule. So here it would, for the CH4, it would just be the hydrogen atoms kind of vibrating, oscillating in place. When we get up here to the 4 carbons, now this bond can spin around right here, and this one can spin around, and this one can spin around. So we've got a lot more opportunity for that molecule to have motion. And so more opportunity, more freedom, it will get messier. Okay. So the big take home is the bigger the molecule, the bigger the structure, the more entropy it will have, the higher entropy, the messier it will be, or the more disorganized it will be. Rigidity of structure. So this one's pretty straightforward, but the more rigid the structure, the less motion it's going to have. So if we have something that is more rigid, it's going to have a lower entropy. Something that's a little bit more free is going to have something that's rigid is less entropy. Something that is structured is more entropy. So here we see your textbook calls them allotropes. So allotropes just tell us that it's the same atom, same state, just in a different form. So the carbon atoms have come together in a slightly different manner. So the big difference between diamonds and graphite is just the rigidity of those structures. So the carbon atoms in a diamond molecule come together in a very geometric shape with very strict angles that are held rigid in that structure, where graphite is a bunch of sheets of carbon that come together. And those sheets of carbon allow for more freedom or more movement between the sheets. So in this case, diamond is more rigid. It's going to have a higher entropy, and graphite is less rigid, a lower entropy. The last thing we're going to talk about is temperature. So increasing the temperature is going to increase the kinetic energy, which is going to increase the motion of the particles. These particles are going to move faster. We also talked about the fact that if we increase the temperature, that typically leads to a phase change as well. So having that phase change also is going to increase the entropy. So this is the reason that if you have a piece of metal and you put it into something hot, eventually those hot particles will migrate from the end that was originally away from your hand and move towards the end that's in your hand. So think about putting a metal spoon into maybe a hot pot of soup and you're stirring. Those particles that are on the hot end of the spoon are going to want to disperse. They're going to want to spread out. So they're going to start traveling up the end of that piece of metal, trying to find a place to spread out into. Well, eventually they will spread so far that they'll reach your hand and it'll touch your hand and it'll start to feel warm. So increasing temperature increases the motion and it makes things messier. So just something to think about, 3 things that will affect the entropy. Hope you guys found this helpful.